Welcome back, everybody. We're to the end of chapter 5, where we're going to deal with complex numbers as potential zeros for polynomials. And that starts us off with the fundamental theorem of algebra. This is actually sort of a big deal. Fundamental theorems are often very big deals. If f of x is a polynomial function of degree n, where n is positive, then f has at least one zero in the set of complex numbers. Counting multiplicities, an nth degree polynomial has n zeros. What this means is basically whatever the degree of the polynomial is, that's how many zeros you're going to have. Now, they may be complex, meaning they may not be actual X-intercepts, meaning we're dealing with the I, a plus bi again, and all that kind of stuff. And so what we're going to do, before we get going on this, I want to throw down an idea. And I want to start with part D, actually. A squared minus plus b squared, pardon me. And we want to factor that. One way to do this, I know it's not equal to 0, but if you put it equal to 0, and we do this, and then we take the square root to both sides, we get that a is equal to plus or minus I root b. And that in general is true, which means our factors are going to be a plus or minus I root b in general. So we went from making it a 0 to making it a factor, meaning this is now a plus root b I, and then a minus root b I. As far as our solution. So this is actually part D here, but I'm going to use part D quite a bit. Actually, with part A, I'm not going to use it. So let's start with part A here. And we're going to factor this over the complex numbers, meaning we're going to get these kind of factors going on here. And actually, these would be our factors. So this factors into x squared minus 5 x squared plus 4. Now we can keep going with this. X minus root 5, difference of squares, x plus root 5. And this one is going to follow this pattern here. A being the x, b being the 4. So this is going to be x minus 2i, right, square root of b. Then x plus 2i. So there it is factored over the complex plane. Complex numbers, part B. And for the this one says complex, we're now just going to factor over the real numbers, meaning we're going to have to stop there. So this becomes x squared minus 5. It's the same polynomial, please note. Minus 5, x squared plus 4. And this is going to have to give us over here x minus root 5, which is a real number, x plus root 5, also a real number. However, I'm going to leave this one as a quadratic. And that's going to be as far as I can go, as far as the real numbers are concerned. And now if we want to take it even a step further and say just rational numbers, C is going to go to here, because root 5 is not rational. That's going to be the end. That's as far as I can go with that. In D, I already did up here. This is a nice little trick that we'll be able to use during the lesson. Part 2. Given a 0, find the other zeros of polynomials, specifically with dealing with complex numbers. Now, if you remember in the previous lesson, if a plus root b was a solution, then a minus root b, its conjugate, is also a solution, or a 0, whatever context we're using it. This is the exact same thing. So if f of x has real coefficients and a plus bi is a 0, then a minus bi, its conjugate, is also a 0. And we're going to utilize that. So example 2, find a polynomial in factored form, meaning we don't have to multiply the whole thing together, which is nice. with rational coefficients that have the following zeros. Let's start with part A. Well, that's going to be f of x equals 0. And remember, it's opposite signs, x minus 3, x plus 7. And once again, they want us to leave it in factored form, so we can just stop there. Now, with part B, because of our theorem here, and actually both of these theorems, we know that 3 plus I is a solution. That means 3 minus I is also a solution. And 7 minus root 2 is a solution. That means 7 plus root 2 is a solution. So this is going to be enormous. And it's a good thing we don't have to multiply it out. This is going to be a lot of work. So here's actually, let's start B over here since we need the space. So here we go. F of x equals, okay, here we go. X minus 3 plus I, x minus 3 minus I, x minus 7 minus root 2, and x minus 7 plus root 2. That is huge. And we could distribute the negatives and change the signs, but there really is nothing to combine. So that's it. That's as good as we're going to get. And I'm glad we don't have to multiply that out. We will have to multiply stuff like this out for this lesson, but we don't have to do it here. Moving on to the next page. Now we still need to remember all of the theorems that we learned from the previous lesson and some of the tricks, because we're definitely going to use some tricks here. Example 3, given that negative 3 is a 0 of this, find all of the other zeros. Before we do that, what I want to do is, let's do our synthetic division. Since we know negative 3 is a 0, so this gives us 1, 6, that's a plus 10, 10, 6, and 9. So remember, synthetic division, we bring the 1 down, multiply, negative 3, and add. 9, 1, negative 3, and that gives us 3. 3 times negative 3 is negative 9. So it really is a 0. So that means this drops down to x cubed plus 3x squared plus x plus 3. And I want to show you a little trick. We're going to use this quite a bit today. So I go to y equals, and I'm going to type in this polynomial. So x raised to the 3rd power plus 3x squared plus x plus 3. And I'm going to see if there's another. So it's either going to be 1, negative 1, 3, or negative 3 as a possibility of factoring it. So I'm going to do this. I'm going to hit vars, y variables, and function. And I put this expression into y1, and I'm going to evaluate it at 1. If I get 0, then I know that it's a 0, but this one clearly isn't. Vars, y vars, function. Evaluated at negative 1. Nope. Vars, y vars, function. Let's try negative 3 again. Negative 3. So negative 3, so there's multiplicity with the negative 3. So we can do it again. Negative 3 now with our new function. So 1, 3, 1, 3. So 1, negative 3, 0, 0, 1, negative 3, 0. So look at that. So this now becomes, so we have negative 3 multiplicity 2 so far, and we're left with x squared plus 1 as our other factor. And we want to set that equal to 0. Well, I can use this previous rule from before. And actually, I could get x squared equals negative 1 x equals plus or minus I. So what are the zeros? X equals -3, I, and -I. And keeping in mind that -3 is a multiplicity of 2, right? We had 2 of them. That worked. All right. So for part 4, that trick that I just showed you won't work with this one. Actually, it could, but we're going to stick to the narrative here. All right. We know that 2 plus 1, or plus I, pardon me, is a factor. That tells us that 2 minus I is also a factor. And we're going to do some foiling and then dividing here. So this means that we know that x minus 2 plus I is a factor, and x minus 2 minus I is a factor. And I'm going to rearrange this a little bit. So this is x minus 2 minus I, and x minus 2 plus I. And I want to point out that I'm going to be using difference of squares. This here. And I'm going to be viewing A as the x minus 2, and then minus and plus, you can see the conjugates there, of I. So this is going to FOIL into x minus 2 squared minus I squared. And remember, I squared is -1, negative becomes +1. Okay, so I know that this will divide evenly into this. So I'm going to do some long division. Again, we can only use synthetic division when we have simple linear factors in the denominator. So we are here. All right, let's start with x squared. Let's use another color. X squared times x squared gives me x to the 4th, and we'll distribute that all the way through. So that's going to be minus 4x to the 3rd plus 5x squared. Subtract. All right, that is going to give me 6x cubed, because it's minus minus. 6x cubed. That's going to give me minus 17x squared. And then we're going to bring down 2x. Now we're going to start again. I need something times x squared to give me 6x cubed. That is going to be plus 6x. Then distribute 6x to the 3rd minus 24x squared plus 30x. Once again, we're going to bring down 35 after we subtract. So that is going to be 1, 2, 3, 7x squared. Let's use another color. That's going to be minus 28x, and that's going to be plus 35. So this is going to become plus 7. Distribute that through, 7x squared minus 28x plus 35, and as expected, we have a 0 remainder. Okay, now what I'm going to need to do, so now what we have is we have that this, I'm getting one space, I'll use the back of the previous page. We have that x to the fourth plus 2x cubed minus 12x squared plus 2x plus 35. So far factors into x squared minus 4x plus 5, which we know give us complex zeros, times x squared plus 6x plus 7. And what we're going to have to do is set these equal to 0. We already know what this is, so really all we care about is that. So we have x squared plus 6x plus 7 equals 0. We already know the two zeros here are these two. So here I'm going to have to use the quadratic equation. So x equals -6 plus minus the square root of 6 squared minus 4 times 1 times 7. Yeah, over 2 times 1. 6 plus minus square root 36 minus 28. 2. So the difference there is going to be 1, 2, 6, that's 8. 8, 2. And factoring out a 2 up top here, we end up with -3 plus and minus root 2. So what are all of our solutions? And I guess I could kind of carve out a niche here. X squared plus 6x plus 7 equals 0. It means that x gives us -3 plus or minus root 2. So all of our solutions are x equals 2 plus I, 2 minus I, -3 plus root 2, -3 minus root 2. 4 solutions. 2 complex, 2 irrational. Part 3. Find the zeros based on the complex number. Now, I'm going to do my little trick again. Y equals, clear that, and type this in. 3x, percent of so you can see what I'm doing, raised to the third power minus 19x squared plus 33x minus 9. Okay. All right. So let's write out all the possible zeros. So it's going to be plus or minus. Up top, it's going to be 1, 3, 9, and down below, it's going to be 1, 3. That's going to give us plus or minus 1 over 1 is 1, 3 over 1 is 3, 9, 1/3, 1 over 3. 3 over 3 is 1 again. I don't have to repeat that. And 9 over 3 is also 3. So this is all of them. Remember, it's twice that amount because it's plus and minus all of these. And so here's what I can do. I can very quickly run through and find if one of them is a real solution. So let's do, so I can go, let's just take it out. That's fine. So I hit vars, I'm going to show you that. Vars, y vars function, function 1, and let's try 1. Nope. Let's try -1. Nope. I know this looks slow and clumsy, but this is actually a lot faster than having to work all these out and do it. Let's try 3. Parentheses 3. There we go. So now all I need to do is, so 3 is a 0. Put my answers up here, 3. And 3, -19, 33, -9. This way we only have to do synthetic division one time. All right, bring down 3. 3 times 3 is 9. Negative 10. Negative 30. Positive 3. Positive 9. 0. Fantastic. So we now have 3x squared minus 10x plus 3 equals 0. So all we have to do is get the solutions to these. Now, I'm thinking that this factors. Great. So 3x minus 1 times x minus 3 equals 0. So x equals 1/3, which we suspected, and another 3. So 3 multiplicity 2 and 1/3 are our solutions. Not so bad. And I know this seemed clunky, but this actually was much faster. All right, last page. All right, find all the zeros. Let's do our trick again. And hopefully we'll be able to find 2 zeros. And first of all, let's load this up. So clear. So x to the 4th minus 8x to the 3rd plus 10x squared plus 24x plus 5. All right, and let's write out our possible zeros, because that's a 1, that's nice. So all we have as possibility is going to be 1 or 5. If it's not one of those, then they're all complex. So let's start. This shouldn't take very long. So again, vars, y vars, function, y sub 1, and we'll try 1. Nope. Let's try negative 1. There we go. So x equals negative 1 is 1. Let's find another, since hopefully we can find 2, so we can drop it down to a quadratic. Because when we have a quadratic, we can use the quadratic formula if we need to. So let's try 5. Yeah, 5 is also a 0. Great. So we're going to do synthetic division twice. So let's start with negative 1. 1, negative 8, 10, 24, and 5. 1, 9, positive 9, 19, negative 19, that is 5, multiplied by 5, and there's our 0. Cool. So this gives us x cubed minus 9x squared plus 19x plus 5. And we're going to run synthetic division again on that. And we know 5 is a solution. We just figured that out because of our fancy little trick there. We got a 0 remainder. So we have 1, negative 9, 19, and 5. 4, 20, negative 1, negative 5, and 0. Okay. So we have found 2 of the zeros, and we are now left with x squared minus 4x minus 1 equals 0. And we can, this does not factor, so we'll have to use the quadratic formula or complete the square. All right, 4 plus or minus the square root of 16 plus 4, 2, 4 plus or minus root 20 over 2, 4 plus or minus 2, 5 over 2. Factoring out a 2 and reducing it, we get 2 plus or minus root 5. Cool. So our solutions are 2 plus root 5 and 2 minus root 5. So 4 solutions, and according to the fundamental theorem of algebra, because x to the 4th power, we should get 4 solutions. Some may be complex, there may be some multiplicities, but we should get 4 solutions. All right, last problem, and then we have a summary. So let's try this again. I'm going to go in, clear that. So x raised to the 4th power minus 5x raised to the 3rd power minus x. This is a problem when we do this. So 5x to the 3rd power, I can remember to hit right on my calculator. Your calculator may not do that. Minus x squared plus 23x minus 6. And let's list out all of our possible zeros. In this case, the coefficient's 1, so that's inconsequential. So we have plus or minus 1, 2, 3, or 6. These are all the possibilities here. So let's go and try to find 2. So we can drop that down to a quadratic. So here we go. I think we can do, yep, and then we can just change it. Now, because we've changed y sub 1, it's not going to be the old y sub 1, it'll be the new one. So let's try 1. Okay, that didn't work. So what I'm doing is I'm going up and I hit enter and it brings it down for me, and then I can change the number, -1. Nope. So I go up there and I hit enter, brings it down, and now I'm going to change it to, let's try -2. Hey, there we go. There's one of them. Let's keep going. So 2 is not. Let's try 3. 3 is as well. Look at that. So we'll do synthetic division twice, like we did up here. Then we'll have a quadratic. Then we can factor it or use the quadratic formula. So here we go. Let's try -2 first. 1, 2, 7, or positive 14, 13, 6, 3, positive 6, and 0. There it is. So this dropped it down to x cubed minus 7x squared plus 13x minus 3. And for this one, we're going to use 3. So we have 1, -7, 13, -3. Bring down the 1, 3, 4, 12, 0. All right. So we have 2 of our solutions, and we now have a quadratic from here, x squared minus 4x plus 1. And this does not factor. So let's use quadratic formula. All right, so we have 4 plus or minus the square root of 16 minus 4 over 2, which gives us 4 plus or minus root 12 over 2, 4 plus or minus 2, 3 over 2. Factor out a 2 and reduce it. I get 2 plus or minus root 3. So our solutions are -2, 3, 2 plus root 3, 2 minus root 3. There are our 4 solutions. And you get x to the 4th, possibility of 4 solutions. All right, so this is a nice little summary of the polynomial functions. If you're going to have to graph one, what do you look for? What can you find? Often finding the X-intercepts, which is what we've been doing this entire past 2 sections, either real or complex. And yeah, so the coefficients have to be real numbers. and the number n is said to be the degree of the polynomial. And analyzing the graph of a polynomial function, determine what happens to the function for very large values of x, for very small values of x. Meaning, if you remember, one of the first lessons in chapter 5 was, does it start up and end up? Does it start down and end down? Is it odd? Is it even? Is Lie coefficient positive? There are 4 cases. You can look back in your notes. I think it's 5.1 where we start with that. The graph has at most n-1 turning points, meaning if it's coming up, it turns and then turns and turns. So it has at most n-1. Find the y-intercept. That's usually very easy, especially if you have something like this. When x equals 0, it's just whatever that last number is, because all the x's that are here go to 0. Is 0 a 0 function? Meaning, can you factor out an x? Is there not just like a number like that? Oops, I skipped down. Attempt to find the x-intercepts or at least approximate them. So for example, with this one, we could get a decimal approximation for those. 2 plus √3. So we would know it's a little more than 3.5, about 3.7, and we could figure out vaguely where that is on a graph. So even irrational ones we can use. And so here we go. A graph has at most n x-intercepts. For example, the previous one that previous two that we just did actually have 4 distinct, 1, 2, 3, 4, 1, 2, 3, 4 distinct x-intercepts. The only time you wouldn't is if you had complex numbers or multiplicities. Attempt to find the x-intercepts. Okay, so is 0 a 0 in the function? Meaning, can you factor out an x to drop the degree down to make it a little bit easier? Is it easily factorable? That's a no-brainer. If it's not easily factorable, then we'll have to resort to other things. And then use the rational zero test to find the paths. So that's where we did this to try to find the rational zeros. At least list them out so you have an idea, and then you can test them either with synthetic division or the little fancy trick I taught you guys using the remainder theorem. And then use the factor theorem to factor out the function as you find the zeros. So there's a lot of good stuff there. That was chapter 5. There's a lot going on there, so feel free to rewatch some of these videos if you need to. Thanks.